of my talk is a complex systems approach to studying the brain on psychedelics. But before I begin, I want to thank Jefferson and the organizers for inviting me to be here today. This work is based in large part on the doctoral thesis of my former student, Aline Viol, whose co-advisor is Professor Draulio Araújo, who works at the Brain Institute here in Natal. And our team also includes Fernanda and Luisa, who work at the Brain Institute. And Aline spent 1 year visiting the IBM Center in New York State, working with Irina and Guillermo. So I will talk about the problem, the motivation, then I will show you the data, the methods, results, and end with the conclusion. The problem we address is how can we understand psychedelics? What happens inside the brain when a person experiences a psychedelic trip? Why are we interested in this problem? It's because there's still a great thirst, a demand for basic research on altered states of mind, including meditation, euphoria, spiritual ecstasy, and so forth, which are phenomena which are still not well understood. Nowadays, we have an abundance of experimental data due to advances in non-invasive imaging technology, such as functional magnetic resonance imaging. And of course, the brain is possibly one of the most complex systems, and any understanding of altered states and so forth will give insight into the neural correlates of consciousness. Finally, there are sociological reasons why this problem is interesting, because psychedelics such as LSD have been used, for example, during the hippie years by famous singers and so forth. It is also fascinating, this is not my area of expertise, but Draulio Araújo, who was Aline's co-advisor, has been studying the use of psychedelics in treating depression, and there is much excitement in this field. So psychedelics can be found, for example, in mushrooms, in certain kinds of cacti. This is the cactus which contains mescaline, which became well known due to an essay by Aldous Huxley called The Doors of Perception. This photo shows a tab of paper that is impregnated with LSD. The psychedelic experience leads to very drastic changes in consciousness, and often there's altered visual experiences. This painting by Pablo Amaringo tries to capture some of these visual experiences. There are bright colors, often snakes and insects and so forth, geometric patterns, etc. The particular psychedelic that we study is Ayahuasca, which is a brew made from 2 Amazonian plants, the leaves of the chacrona plant and the vine mariri, and ayahuasca has been used in the indigenous cultures of the Amazonian region for quite a long time. Ayahuasca contains several psychoactive substances. One of the more important ones is dimethyltryptamine. It is a tryptamine hallucinogen of the same family as LSD and is chemically and structurally related to serotonin. Now, tryptamine is a monoamine compound, and our digestive system contains monoamine oxidase, which metabolizes DMT quickly. So if you ingest orally DMT, there is nothing left to cross the blood-brain barrier because it is metabolized in seconds or minutes. However, ayahuasca also contains this other plant, mariri, which has an inhibitor of the monoamine oxidase enzyme. So the 2 plants taken together have a strong effect because the monoamine oxidase inhibitor stops the enzyme from breaking down DMT, which then can cross the blood-brain barrier and exert the powerful psychedelic effects. This is a photo of the brew, and this is the drink. It looks like dark coffee or chocolate. The psychedelic experience usually lasts about 4 hours. And another reason we chose ayahuasca and say not LSD or mescaline is that ayahuasca has legal status in Brazil since 1985 for religious and scientific purposes. Okay, so let me show you the data. The experimental procedure for collecting the data was designed by my collaborator, Draulio. He's a specialist in nuclear magnetic resonance imaging. And the key quantity is the bold signal, which is the blood oxygen level dependent signal. It's a standard MRI, fMRI signal, and is a proxy for brain activation. When a certain region of the cortex of the brain is more active, very quickly it leads to more local oxygenation, and the bold signal can pick up this change, and so we can see visually what the brain activation looks like. The data consists of 4-dimensional images, 3 spatial and 1 time dimension, with a spatial resolution of 1 to 8 millimeters cubed and a temporal resolution of 1 to 2 seconds. Our data consists of approximately 10 gigabytes. So 9 healthy adult volunteers took 120 to 200 milliliters of ayahuasca and entered the MRI machine before taking the ayahuasca and also 40 minutes after taking the ayahuasca, and everybody was awake and at rest. So how do we analyze the data? There are many steps to analyzing the data, so let me give you an overview and then I will describe each step in some detail. So, the scans are divided according to different brain regions. Using a standard atlas of the brain, the scans were divided into 110 regions of the cerebral cortex. And for each signal, we have an average bold signal. And using the bold signal and looking at pairs of regions, we can look at cross correlations. And using all possible pairs, we build a correlation matrix for the bold signal from the different regions of the brain. These correlations can range from -1 to +1. And we take the absolute value of the correlation and use a thresholding procedure to create what is known as an adjacency matrix, which only consists of zeros and ones. And these adjacency matrices, which I will show you soon, are mathematically isomorphic to networks, complex networks. And so then we can use standard complex network methods to characterize and compare the networks before and after ayahuasca ingestion. Using a thresholding procedure. I will show you in a little bit. So these are, for example, if we have a complex network where we label each node and the links can possibly connect the nodes, the adjacency matrices contain the information about the links. A 0 means there's no link between a given pair of nodes, and a 1 indicates that there is a link. Let me also introduce some other key quantities of interest. The degree of a node is simply the number of neighbors to which it is linked. So for example, this node has degree 5 because there are 5 links attached to it. And if we make a histogram of the degree, then we can obtain the degree distribution. And there are different kinds of degree distributions. For example, scale-free networks have power law degree distributions and so forth. We also looked at the geodesic distance, which is defined as the minimum number of links that you need to traverse between any two nodes. So for example, between node number 5 and 9 over here, you have to traverse 3 links at least. And so this is the geodesic distance between these two nodes. And we can define the mean geodesic distance, which is the average over all possible pairs. The clustering coefficient is another key quantity and is a measure of how clustered the nodes are. Are the neighbors of your neighbors also your neighbor? Or, for example, if you have a social network, are the friends of your friends also your friends? And the clustering coefficient can be calculated from the adjacency matrix A using this expression. We also looked at efficiency, which is a measure of how easy it would be for information to spread if the information could spread in this kind of network. The global efficiency is defined as the reciprocal of the harmonic mean of the geodesic distances between all pairs of nodes. And the local efficiency is defined in a similar way, but only for the subgraph of the neighbors, of the first neighbors of a given node. The key quantity that we looked at is the Shannon entropy of the degree distribution. It is given by this well-known expression and was introduced in a seminal paper by Claude Shannon, who was studying communication channels. If you measure entropy using base 2 logarithm, then the Shannon entropy is measured in bits, but we use the natural logarithm, and so we measure entropy in natural information units. We used more sophisticated methods, which I will skip due to lack of time, but I will be happy to discuss them later. Okay, so here is a more detailed summary of the method. So after filtering and pre-processing the data, we take these approximately 100 cortical regions, which have an average bold signal, and then we look at the correlation matrix, and then we use a threshold to generate the adjacency matrices. How does this thresholding work? So this was your question. So these correlation matrices, once you take the absolute value, the elements range from 0 to 1. If you use a threshold in that value, you can use a step function to transform this matrix of fractional numbers into matrices consisting only of 0 and 1. If you use a very high threshold, then you will get a very sparse matrix, which means you have a sparse network. If you use a low threshold, then almost every pair of nodes will be connected, and you will have a highly connected network. The particular way to choose these thresholds is somewhat complicated, so I will skip the details and show you the main idea. Please. The same threshold for every pair of nodes, yeah. Yeah. Mm-hmm. Yes. Mostly the cerebral cortex. Mostly the cerebral cortex. Yes. Uh-huh. Yes. Mm-hmm. Okay, so for each of the subjects, we only were able to use data from 7 subjects because for 2 subjects, the data were not good enough. Their heads were larger, and it was difficult to normalize the data. But for these 7 subjects that we had good data, using these correlation matrices, we used 16 different values of the threshold to generate 16 different networks. Each network has a slightly different mean degree for the nodes. And we used more sophisticated methods, which I won't talk about, so let's just focus on these networks that we generated for each subject before and after taking ayahuasca. Okay, so the results. Here's a summary of what we find. The main result is that after taking ayahuasca, there is an increase in the Shannon entropy of the degree distribution of the functional networks of the brain. We also found an increase in the clustering coefficient, an increase in local efficiency, which point to higher local integration of the functional networks, and a decrease in the global efficiency and an increase in the mean geodesic distance. That means the networks are qualitatively speaking larger, and this points to decreased global integration. Here's an example of the degree distribution. So the vertical axis shows histograms, and here you have the degree of the nodes. For one subject before and after taking ayahuasca for one particular value of the threshold, and what we see is that after ayahuasca, the distribution is wider. So this is why this is compatible with the higher entropy for the node degree distribution. So let me skip some of these slides and show you the entropy. So here we have the 16 different mean degrees corresponding to the 16 different thresholds. And the vertical axis shows mean and standard deviations before and after ayahuasca for the 7 subjects. And you see clearly an increase. The green is after ayahuasca, the blue is before ayahuasca. The same results here are shown in a... Yes. Yes. Here is the same data now shown per subject. So we have these 7 subjects, and we have before and after. The blue is before, the green is after ayahuasca. Values of the entropy, these are box plots, so the red line is medians, and these are quartiles. And the average is over the 16 values of the thresholds. If we look at the difference in the entropy per subject and per threshold, this is the box plot, and you see, here is 0. This would mean no entropy increase over here. So for all subjects, we see an increase in the entropy, and the results are statistically significant if we use a p-value of 0.005. The absolute value of the entropy?
Yes, because you see the initial value is very different.
Yes.
Does it have any value or just the difference that's important?
This is a fascinating question. I'm not a specialist in the subjective states of mind, but Dralju has looked at how entropy correlates with questionnaires, the results of questionnaires of mental states such as dissociation, tendency to be depressed, and so forth. And there is a very strong correlation. But I'm not going to be showing these results today. But it's a very good question. Yeah, I understand your question. You're asking, could this be a placebo effect, right? Is that? Whether the results are culturally dependent. Yes, I don't know the answer to this question. Okay, so let me continue and we can get back to this in a bit. So very clearly we find evidence of entropy increases for the degree distribution after taking ayahuasca. Let me try to, I have many other results which I cannot show for lack of time, but let me try to put these results into context. So what can we say about this increase in the entropy after taking this ayahuasca, which is a psychedelic substance? In 2014, Cahart, Harris, and collaborators proposed a hypothesis known as the entropic brain, where they argue that there is a big difference between the ordinary state of mind and the psychedelic state of mind, which can be understood in terms of a difference in the entropy of the functional connectivity. In the following sense, they propose that in the ordinary state of mind, our mind and brain functions are following a highly trained, learned mode of behavior with many, many constraints. So for example, just to make it clear, it is many thoughts are socially unacceptable at dinner table, for example. And so you constrain, the brain operates under certain constraints. However, when you're in a psychedelic state, many of these constraints are removed and thoughts flow more freely and don't have to obey, for example, the rules of grammar or social norms, etc. And so in this sense, there are fewer constraints in the operation of the brain in the psychedelic state. And since entropy measures information, we know that low entropy means that there are very few possible configurations for the system. And high entropy means that the system can be found in many, many different states. So they gave a name to this hypothesis, which became known as the entropic brain, which claims that the psychedelic state is associated with higher entropy. So, to conclude, our finding of higher entropy, Shannon entropy of the degree distribution of the functional connectivity of the brain is compatible and supports this entropic brain hypothesis. I just want to make one small comment. This idea that the ordinary state of mind is a secondary state of consciousness rather than a primal or primary state is actually found in the writings of the philosopher Alan Watts, who was looking at how the ordinary state of mind compares with meditative states of mind. And so there's this connection between the psychedelic state of mind and meditative states of mind. Okay, so thank you very much.